Very good. So thank you, Venki. And I was saying I'm really happy and excited to be here. As I was saying, we opened the first session. I think this is really a great opportunity for us to, to discuss and to tell you more about our solutions for acoustics. So we thought today to go through an introduction about the platform. And recall some of the basics, and then we will go into doing a bit of summary about some latest Fluent advances. So in this session, we will focus more on the sound generated by the fluids, and then we will go with Milan to talk about ANSI sound that as a Dr. Venki was recalling. This was basically coming from Genesis before, and then with Banu we'll go more talking about some application examples, showing you in action how these tools can help to solve let's say real problems, and also Milan will show some nice examples. And then we are happy to to discuss and have questions and follow up on this. So to start with, I would like just to to introduce you about the framework where we go to hold our discussion and speech today. So in ANSYS, as you might know, we have different tools, and we can cover different physics. For example, we have structural analysis that we can do with ANSYS Mechanical, but you might also hear that we have Maxwell. This is our tool to perform electromagnetic analysis. So considering these two tools together and being able to couple and having developed some specific NVH workflow, we can deal problems like vibroacoustics problems, and a classic example is also like electric motor as an example. Then today we will focus more on the fluids part, and you know very likely that our main tools for this in ANSYS is ANSYS Fluent, and so we will spend more time in this session today to talk about what you can do with ANSYS Fluent, how you can predict aerodynamic noise, and also how you can interact also the fluid simulation with structural simulation and with the rest of the platform. But we also have some tools which are very good to compute body dynamics and multi-body dynamics, like ANSYS Motion. An example still, to remind about electrification is, for example, gearbox motion, which part of it is really due by this multi-body dynamics and contacts between the parts. And last but not least, we have also LS-DYNA, which is quite known in the automotive domain for crash analysis, and it has also some other powerful solvers like BM solver, and we also have like statistical energy analysis tool for acoustics. In this case, we are showing just a picture about an example of application of LS-DYNA to compute impact noise simulation. So we use LS-DYNA for its, let's say, structural dynamic capabilities, and we showed in the first session, we showed also some examples of this application. So all of this, in addition, also with measurements and test data, can be fed into our platform for acoustics, which is called ANSYS Sound. So ANSYS Sound is our platform where we can connect not only the simulations, but also the measurements and real data to be able to listen to the sound, to be able to analyze, for example, computing psychoacoustics indicators and trying to analyze how the human being is perceiving this sound, and then we can compare the sound. You can compare different designs, but you can also compare, for example, a simulation with experiments. So you can try to, also to understand which might be some of the differences. Or you can also use this tool for to optimize. Optimize, we mean you can optimize your design, but you can also optimize your target. So you can use ANSI sound also to make some analysis in order to say, okay, what if my target, I have this tone which has a lower level. So then will I be able, as a as a human being, to perceive it really or not? And so it is also helping to set some targets which are also useful for simulation. So as Dr. Venki was recalling, this platform, some years ago, it was founded by Patrick Broussard, and it is Genesis basically, and it was more related with measurements. So what we have done in these years with a very exciting project is really to extend this platform and to further develop to take both simulation and measurements. So now I will just have a really brief introduction about acoustics, aeroacoustics, and about some terminology that we will use also later on. So for aeroacoustics, with this term, we really mean the sound which is generated by the interaction of a moving fluid flow and any object, or even with just the sound generated by the fluid flow itself, like self-generating noise. So here we have different kind of noise that we can compute. As just as an example, if you consider the interaction of the air with a fan, we can have fan noise, we can have wind noise. Turbulent jet noise is a classic example of self-generated noise where you don't have, let's say, a surface where the sound is being, let's say, generated and scattered. Or you can have also other kind of noise like resonance, noise in pipes, or you can also have noise generated by shock waves. So the compression of due to the shock waves then is generating this famous sonic boom. So this is one area, but if we add also on the top of it mechanical vibration to the problem, because in reality, very often when there is a structure, there might be some strong impact of the structure in the propagation or even in amplifying or reflecting the noise. So in this case, if we have a strong vibration contribution, we talk about vibroacoustics, okay? And if we add the fluids noise with mechanical vibration, we go to a more complete problem, which we call aero-vibroacoustics, which is generally called aero-vibroacoustics. And we'll show some examples of this. But now, let's say mostly you can have as your medium is air, but you can have also like water. And we will show some nice examples also of this application with Banu, and here we have what we call hydroacoustics. So you might have heard that performing aeroacoustic simulation, so extracting the sound from the flow, can be quite challenging application. Indeed, we consider it a little bit of leading edge application because first reason is because very often, apart from the cavity resonance problems, or generally any resonance problems, very often the acoustic wave magnitude is very small compared to the aerodynamic or hydrodynamic pressure. And so you have to compute and then propagate this very tiny fraction of energy of the flow. And so you need, very, very good numerics, and you have to be careful about every detail of the simulation, like the mesh, like the numerics, and so on. The other thing is also that you have quite a large frequency range, which is also the human being an ear frequency range. So you go from 20 hertz up to 20 kilohertz. Of course, not in all the simulation you are interested in this big range, but so you need also to be very careful about the temporal resolution, and this has to be small enough to be able to capture also the smallest frequencies that are generated in the flow, and also being able to propagate it. The other things is sometimes for the grid, for the mesh resolution, let's say the constraint, the minimum grid constraint is not directly the acoustics, but it is a turbulence. So you need to capture really the details of the turbulence to be sure that you are accurately computing the sound out of the flow and of the turbulence. So very often that is one important part that is addressing the accuracy of how you perform and you simulate the generation of the noise. And so to do this, you need high fidelity numerics, turbulence models, accurate turbulence models, and also you need some acoustics models in order, in some case, to simplify the problem. And we will show very briefly what we mean by that. But here is just a collection of real use cases of validated simulations that we have performed. And here you can see we can go from fan noise case, blower acoustics, electronics, cooling, but you can also go into combustion noise problems. We will show examples about side window noise. An example is automotive, but you can imagine this to be applied even to a landing gear or even to a 5G antenna. We have done application like that. Then there is also a class of problems regarding the propagation inside, let's say, a cabin. And the cabin can be automotive cabin. It could be like a train. It can be like a drone or helicopter. So these are similar in how you approach them. Then you can go to propeller noise, and here we also have validations even with transonic propeller now, and I will talk more about the new trends we see, like drone noise. And then we have like supersonic jet noise and wind turbine noise. So you can see here some nice animation of the flow, and we will have a bit more discussion on jet noise, impinging jet noise, and some of these applications. So let's go and also talk a little bit about which are some of the trends that we see in aeroacoustics, with particular focus on transportation and electrification, which is as we know, a relevant big trend that we see everywhere in the industry. So first of all, in the electric vehicle comfort, of course, if you can see on the left, you have these two charts which are showing that in an internal combustion engine vehicle, this gray part, which is powertrain, was almost, let's say, 50% of the noise which is heard inside the vehicle. But now with electric vehicles, we have electric motors, and they are generally much quieter. So we have reduced this noise, but you might also have experienced that then you start to feel and perceive and listen the other noise sources. So all the other noise sources are becoming now in some way more relevant because they are less masked by the powertrain noise. Of course, this subdivision, then it depends on the speed. If you go at a very, very high speed, of course, then the wind noise will become also a very relevant noise source. If you go at the moderate speed, this is more like these charts, they refer more to medium to low speed. So then we see another big trend. It's electronics cooling. So we see more and more, HPC clusters growing, and also GPUs, and we see this also in the automotive. Lots of the ADAS or other sensors now they all are driven by very strong CPU, and in particular there is a big demand for GPU, which can do some high speed in real-time computation. Then another trend that we see, and we see more and more, let's say, industries and customers interested, is to simulate the real-world problem, which is aero-acoustics. So very often, let's say, up to a few years ago, these problems were often, let's say, approached in a separate way. So I do the fluid dynamic part, and then separately I do the mechanical part. But some problems are really coupled, and you want to do all this together. And then we see some nice trends for propeller acoustics and increased demands for drones, and also it's still not around us the city taxi, but lots of industries are already working on designing these concepts, and so we have been involved in some activities with some very important customers that are already working on prototypes of city taxis. So, but how we address, how we approach, how we solve the problems and the challenges that I briefly mentioned before. So we have a set of methods in Fluent. So the first one on the left, it's broadband noise, and this is basically using RANS simulation. So it's Reynolds average Navier-Stokes. So it's quite cheap. It's the cheapest effort, and it can give you some qualitative information. It's not very accurate, but it can tell you, in particular, the noise generated by turbulence itself. So the quadrupole noise source, where are they located, and also you could also do some compare two configurations. Very often this is very relevant for high speed, because what is dominant at low speed and let's say a low Mach number, let's say typical, for example, of automotive, is more the dipole noise source, which is related with the interaction of the flow with the structure. So let's summarize, broadband noise, they are more related to quadrupole noise, and it is the cheaper approach. Then you can see on the bottom right, we have the acoustic analogy methods. Here, the idea is that I can compute the noise sources, and then I do the propagation with an analytical formulation. In this case, I am assuming that the problem can be decoupled. So the noise source is decoupled and not being influenced, and vice versa, by the propagation. So here the assumption is I don't have any obstacles between the source and the receiver. This is also suitable when your receiver is placed very far. Okay, so if for example, you want to know what is the noise of a propeller, and the propeller is a propeller, for example, of an aircraft, and you are 2 kilometers far away, or you are even just in an airport and you are 500 meters far away, you really don't want to go and mesh all the fluid domain for 500 meters. Okay, so this is one typical application. You have to be careful because the problem is not coupled. In particularly, you are not going to address resonance effect, like cavity resonance and this kind of problems, because they are inherently coupled between the propagation and the noise source. Then we have on the top left part, we have the direct methods. And here, for direct method, we mean in the Navier-Stokes equation, there are all the ingredients to really compute the noise which is generated by the flow and the propagation. Generally, this is used when the receiver is not too much far away, because you have then to do the mesh up to the receiver. And the other class of problems is when you have a strong coupling between the noise generation and also the propagation, and between the flow itself and the sound generation, where you cannot decouple the two. An example is like resonance effect. Then on the top right, then we can give the possibility to couple this fluids aeroacoustic methods from Fluent. You can couple this with ANSYS tools, but you can also couple with external tools. And last but not least, we can also listen to the sound, and this is a capability that is a direct influence. So this is just an example. This has been directly computed with Fluent itself, and by the integration of ANSYS sound, as I will show you in Fluent. And I also wanted to mention this really exciting project that we have in Fluent, and the first release will go in next January. So basically, it's 1 month from now. Is a multi-GPU solver. So as these simulations, and in particularly high-fidelity transient simulation, are becoming more and more challenging in terms of computing performance, we have developed a dedicated multi-GPU solver in Fluent, which can drastically accelerate simulation. Let's say we have factor which can go from 5 to 10. And noise prediction is absolutely in our roadmap, and it is under development. The first release will be really setting the basics more for external aero and not for acoustics. But in the next release, and we're already working, and we have this goal in mind, is about aeroacoustics, to be able to do with a GPU solver. So let's stay tuned on this. And now, I will just recap some of recent capabilities that I think in the last couple of years we have made really great progress, and I'm happy to share with you also, because this progress are really relevant to the applications that we will show later on. So we have released in 2021 this new deterministic aero-acoustic workflow, which we will discuss a bit more in detail later on. And it is basically coupling the fluids with mechanical acoustics for doing what I described before, called aero-acoustics problems. Then we have a new impedance boundary condition in Fluent, and this is quite unique for a CFD solver, because we can set impedance boundary conditions. So you can also take into account, let's say, absorption material. Generally, CFD is always done with the hypothesis that the walls are fully rigid, but this, from acoustic perspective, this is very often overestimating the noise. And then you can also input data in the same way as you would do, as you get from the experiment. So you can put basically complex impedance tabulated data. And then I will talk you more about, we have integrated some capabilities from ANSYS sound directly into Fluent, and an example was the possibility to generate a sound file directly from Fluent. Other interesting capability that came this year are a sponge layer to dump the acoustic sources and noise generation. And we have also an example with Aeroacoustics from Banu. Then we have this exciting project about runtime discrete Fourier transform. So we will compute the discrete Fourier transform at the runtime, and then you will be able also, and you are also already able to do inverse discrete Fourier transform, so to reconstruct the signal in time based on the frequency range you are interested in. And then we have transfer function and sound composition capabilities, which come from the integration of ANSI sound directly into Fluent. So these are the three other big relevant milestones. And talking about ANSI sound, I've showed before, you know, the introduction about the platform, but how it is integrating in the Fluent workflow. This is just an example. So ANSI sound can help to identify the targets for CFD simulation, for example. ANSI sound can provide also frequency response function and input files that can be used by Fluent. Then Fluent can perform aeroacoustic simulation at, for example, component level, for example, like an HVAC system. And then we can use ANSI sound to do advanced post-processing and also to enlarge the picture, and this will be shown later on, to compose different noise sources altogether, because ultimately, like in a car, what you hear is not just an isolated noise source, but you generally hear multiple noise sources altogether. So just to remind about this Fluent capabilities of ANSI sound, what you can see on the right is it's a Fluent panel, but you see that you can already read it ANSI sound analysis. So this panel can be popped up by Fluent, and just to mention some of the capabilities. So you can listen to your sound simulation. You can see here circled with a dark yellow. You can generate wave files from. You can also generate basic psychoacoustic indicators, like in articulation index, for example, which is important for speech recognition. Then you can use frequency response functions, which are being computed by ANSI sound, for example. And then you can directly launch ANSI sound from this panel, and it will transfer files. And so we have a nicer, let's say, workflow in terms of usability for going from Fluent to a more advanced post-processing analysis in ANSI sound. So at this point, I will pass the ball to Milan for an introduction about ANSI sound.
Thank you, Domenico. So yes, this is a small introduction to ANSI sound, because you heard Domenico talk about it quite a lot, and because there will be more talkings about ANSI sound in this presentation. It's good for you to know that it's let's say it's a standalone software from ANSYS that is not doing simulation like you could think of ANSYS software. So it's more like a post-processing tool for acoustic and vibration data. So those data may come from simulation, CAE, or tests. And you will have to listen to the data, to compare the data, but also to apply transfer functions, operating conditions like rotation speed or versus time, or temperature versus time that can make a sound vary with time, and also to apply masking noise. And the goal of ANSYS sound is to gather everything, simulation coming from different noise sources, to assess the sound at what we say at system level, so taking into account all the sound sources together. So in the next slide, there is a small video of the interface, so you know how it looks like. And basically here, you first start to load your data. So here I will open a WAV file. which is a simulation actually of a fan. But also you may want to import samples as text files to also import some spectrum that you have calculated. Okay. And after you load your data, you can do this, let's say, standard analysis. Oh yeah, here you can also generate a signal from a spectrum, generate a signal from a waterfall, but you do this standard analysis where you first calculate a spectrum in different formats. So I saw a question about how to calculate dBA from dBSPL. So here you can do it. You can switch to dBA in spectrums. You can switch to logarithmic frequencies and then place cursors and see the values, etc. But also in terms of time frequency domain, you may want to look at your data in a color map. So with the frequencies on the y-axis, the time on the x-axis, and the color and the scale so amplitude as a color scale. Small feature that I've added in this video also is to be able to do some sound troubleshooting, meaning, so here's the sound again. Sound troubleshooting, meaning that you may want to modify or isolate part of your signal in the time frequency domain to assess the sound if this part that you selected wasn't there. Yeah. So here I have a main, let's say BPF, blade passing frequency at 200 and 500 hertz, more or less. Yeah. So after I select this part, I can, let's say, first isolate. But also I can do rub out, so assess the sound if it wasn't there. This is without. Okay. So after this, you can do all this type of post-processing with calculating psychoacoustic criteria, so standard levels or sound quality levels of those signals that you've imported and that you've modified. And I'll just show that in this video. So in modules, you have the psychoacoustics module, also frequency response estimation module, and all sorts of module. And here I will only show the psychoacoustic modules where you have to click on the indicator that you want to compute for your data. So I won't compute everything, but only dB, dBA, the loudness, the sharpness, and the tonality also can be good for this application. And then you can compare and look at the sound quality of your data. And yeah. Also in terms of time domain, yeah. We can plot them versus time. That's it, Domenico.
Okay, thank you, Milan. Very good. Let's go to next section. Now we will just go quite briefly to show you some application examples with ANSYS Fluent and ANSYS Sound. And if you have any other kind of problems, we are really happy if you get in touch with us. So up to Banu.
Thank you, Domenico. Hope I'm audible.
Yeah.
Thank you. So thank you, Domenico and Milan, and I'll just continue the rhythm. And first application I just wanted to point out is aerodynamic noise. And though we are showing this as a an automotive application, but this is relevant to multiple industries and maybe not just the automotive. It could be high tech, or it could be transportation, it could be aerospace, and the defense also. So for taking this example on the noise over the cabin, the automotive cabin. So first of all, this application itself is gaining a lot of importance, and as Domenico mentioned, that the IC versus EV is gaining a lot of importance, and this becomes a very critical application. Now, typically we are engaged in such type of application for predicting the noise on the scowls, on the A pillars, or on the side mirrors, and how the modification of these designs can affect the results, affect the noise levels inside the cabin. And for this, we have a very robust solution. And first important aspect is the turbulence model, and Domenico pointed out that in aeroacoustic turbulence plays a major role. Now, LES can be one solution, but being expensive, we have some of the best scale resolving turbulence models like SBES, which is uh, a combination of the scaled the RANs and the LES models, which can give us very good accurate solutions. And then, as these are some computationally expensive large meshes, HPC scalability is very important, and Fluent has always been investing a lot from years on the HPC scalability, and we show a very good scalability on the computational front also. And then once you have these expensive solutions, if you are not able to figure out some of the good results, critical noises, post-processing, it does not make sense. And hence we have been focusing for at least for last 2-3 years, we have made a major improvement on the post-processing part of Aeroacoustics and Fluent, which increase coming in IDFT, DFT, some noise source localization, and eventually some of the NSYS sound features coming in into the Fluent. So that is some of the very important aspects which have been focusing about these application. In fact, we had Domenico had a recent publication for this, and it was an old public work, but then he reinvented the wheel with some of the latest technologies on the numerics part, some meshes, and you can see on the right hand side at the bottom the accuracy of the results on the noise pressure predictions on the side mirror at different locations, and it is very good accuracy, I can say that. And if you see the benefits, the solution level is that you can turn this around in 1 or 2 days depending upon the combination of accuracy versus the design iteration you want to do. So we have some different methodologies in place, robust methodologies in place, where we can decide whether you want to go for a high accurate solution or maybe faster design iterations, and we can play around with the time step sizes, inner iterations, and get the solutions as per the requirement. So accuracy or time, whatever you decide, we have all sorts of methodologies for those. Yeah, so maybe to the next slide. Now, once you have this wind noise, the second a second example or a logical step would be the prediction of noise inside the cabin. Now, again, I will reiterate, though this is an automotive example, but it is relevant to all sorts of industries. It could be for transportation, like Domenico mentioned, on railways or aerospace or defense cabins, or it could be heavy moving vehicles where the cabin noise is sometimes more prevalent, or in fact, I can look at it from a different perspective. If the noise is traveling from the outside to interior or from interior to outside, for internal flows also, DAWA always plays very important role. Now, having said that, what is important in this is that, in fact, in this specific example is that the wind noise, how it is finally perceived inside the cabin. And that requires the propagation of the noise, the wind noise into the interior, and that passes through the wind or through the side mirror, and that requires some mapping, some coupling mechanism. And we have a robust coupling mechanism in place where the spectral data is mapped onto the outside of the mirror, which propagates across the side mirror and goes to the in-cabin. So this DAWA approach, which is deterministic aero-vibroacoustics, is quite an accurate solution for that from that perspective. And if you see, this is a validation study which has been done, and up to 5 kilohertz, we get a very reasonable accuracy from test versus the experimental data. Now, This type of application sometimes can take some time because they are computationally expensive. It can take some days to complete the whole workflow when we talk about the fluid and the mechanical coupling, and then finally the mechanical solution. But then the next logical step would be, how do we reduce that time? How do we not every time do that solution, and rather we have some other ways to use our already developed CAE data and get that solution. And for that, this is one of the solution which is very robust, which is like generating the frequency response functions. Now, what you can do is, based on your input data, which can come from your CAE, from a system level, a component level to the system level, or maybe from some experimental data, and you generate your frequency response functions. Now, once you generate your response functions, which typically would be possible only through ANSYS sound, you can then use those response functions, and with the new developed CAE data, using these frequency, you can predict the next output of without running the CAE simulation. So that is one of the and which would eventually means a very small turnaround time, maybe in seconds, to predict without running the whole CAE simulations. So what can happen is, it can be system level prediction. So moving from system level to the component level. For example, if you take this on the right bottom, what has been done is there was one complete DAWA workflow done, which was the previous similar study where the fin noise was done, then the coupling was done, and eventually the final prediction in the inside the cabin was done, and then the frequency response function was generated using sound, ANSYS sound. And then again, a different operating condition in cabin noise was predicted using this FRF function. And again, and also one complete DAWA workflow with the modified design was done. Typically, the operating condition was not changed in this case. It was the side mirror design which was changed, and then the prediction of the noise was done. And I can tell you the accuracy of the FRF versus the simulation was quite in principle the same. So you can think of doing one simulation, the complete workflow, generating an FRF, and then next time you modify the design on the side mirror, and then predicting using the FRF would be quite accurate. So that is the advantage of using frequency response functions. In fact, not just frequency response function. Domenico, I just wanted to highlight one more point in previous slide. You can also go for sound composition. So there would be scenarios, and as we see in our system level simulations, it is just not single noise source. There are multiple noise sources. It could be, for if I talk about automotive also, it could be tire noise, it could be the e-motor noise, it could be the HVAC noise, it could be the wind noise. Eventually they have to get composed to understand or perceive the actual perceive quality of the noise that the driver or co-driver will receive. And Milan would be highlighting that how the composition of the noise can be done along with fluent combination enhances sound. Right. Yeah. Now, having talked about the system level, how we moved from a small from a one analysis to the system level design, and how we can use the frequency response function as an advantage from moving from component to system. One thing still remains important is that we focus on the component level simulations and the accuracy of the simulations. And this is one of the example. It is a very good work in combination, in collaboration with Tata Motors we did. And one important point is this is an application of a rotational flow. Now, till now, we didn't see a rotational flow example. This is a rotational flow. And though this is an automotive rotating flow, it could be relevant to, again, drones. It could be relevant to aerospace industry, HVAC, high-tech industries. You, in principle, the phenomena, the methodology would remain same. Only the calculations would modify based on the frequency of interest, the RPMs, and different operating conditions. Now, in this case, if you see the turbulence model again used was GECO SBES, which is the one of the robust latest methods. Though this paper, which was published, if you see on the right side, was around 2018 or so, there has been much more new developments that has gone in. from numerics perspective in Fluent and from post-processing perspective. So I would say this to be after 2 to 3 years still to be an old paper, not a new paper, because much has changed in Fluent from there on. And if you see the turnaround time for this solution, it's just 1 day on 512 cores on 35 million cell count. And you see the accuracy of the results on the driver and co-driver level, quite in principle, almost matching within the deviation of 0.5 or 1 to 2 dBs. And definitely the outcome would be on the component level, you want to identify the noise sources. So that feature is very important. That is one advantage of CAE versus the experimental that we achieve on these type of simulations. And then definitely you can at the early design stage improve your designs without going into the prototype level, and you can achieve maybe 2 to 3 dB reduction also. Dominic, the next slide. This is another example of internal flows. So I think there was one question on a very similar application, that can we model the multi-phase for the evaporator noise. But this is not an example of multi-phase, but definitely that can be done. But what is important in this, very similar to what was asked in the question also, is the internal flows with real gas modeling. Now, this is an example of how the noise from the pulsating noise from the compressor moves upstream to the evaporator, eventually passing through the evaporator to the HVAC system and going into the cabin. So sometimes the muffler treatment works and sometimes it does not work. And such type of simulations requires can be very useful to see the possibility of putting up a muffler, or which design would be better under different operating condition. So this is one example, and transmission loss is one of the important outcome that we look at. So if you see the turnaround time, I would say is around 24 hours to get a design iteration. And important part is that you can model the real gas flow, real gas phenomena, because it's a refrigerant that we are modeling in. And you can save a lot of cost at early designs. And I can tell you, there is no way you can actually predict the noise in testing also. It is more of a qualitative testing that is done to see if muffler is important for given applications or not. So again, an internal flow with low Mach number flows with real gas modeling, important for all other process industries, and wherever internal flows are important can be done. So we are picking up only specific examples due to the time constraint, but definitely you can approach us with your problem statement, and we definitely will discuss and see the possibility of how it can be modeled. Right. Next slide, Dominico. Right, this is another example, a very different physics perspective. So till now we have been talking about low Mach number flows or low speed flows, the noise generation, but definitely Fluent as a solver is capable of predicting the high speed flow noise also. So this is like supersonic jets noise or screech noise, which needs to be captured, which can be easily captured, very relevant to the defense and aerospace industry. In this example, it is more to do with, as the takeoff happens, how the bottom plate gets affected, the plate gets affected by the acoustic waves, the structural integrity study of the plate which is at the bottom. Now, this is again an example of a DAVA workflow, very similar to what was shown for the aerospace industry, for the automotive industry, where you solve the high speed flow on the ANSYS Fluent, map the pressure spectrum on the bottom plate on the as jet impinges, and then do the resonant study of the structure. So typically, if you see on the right side the accuracy of the result, the first map shows more of the hover lift loss, which is more to do with the convective flow field accuracy. But if you see the below plot, it is more to do with the accuracy on the acoustic front, which is at, if you can see, the highest frequency that is being resolved is at order of 20 kilohertz for such a high speed flow, which shows the capability of Fluent to predict high accurate solution for complex physics. Right. So high speed flows definitely is one of the example. Now, this is another point which Domenico was mentioning, that till now we have been focusing on the aeroacoustics, where air is should be the medium for generating the noise, propagating medium, and finally perceiving it. But a lot of defense and marine applications, underwater acoustics are where the noise generation and propagation happens due to the fluid, which is water. Now, what changes there? Typically, the speed of the sound changes, right? In principle, the speed of sound for the water is around 1480 versus the speed of sound of air is in the air is 340. Then water is maybe effectively treated as incompressible, but definitely Fluent has that capability of modeling the compressibility of the water also using certain equations like date. And then what is important underwater acoustics is the complex water environment. Now, when we say complex, the gradient of the temperature, the gradient of the density with the height, and also there are some sediments, free surfaces, and cavitation involved. So that increases the complexity of the environment which needs to be modeled. And for that, Fluent has been used as a solver to compute both CHA, which is compressible liquid, which is more similar to CAA, which is computational aeroacoustics. The direct method can be implemented with compressibility of the liquid. Or you can also have FWH formulation to be implemented on hydroacoustics application also. And if you see on the right side, this is one of the example, which is a marine propeller. The convective flow field being quite accurately predictive, and you can do the directivity study, but I have just shown one of the plot of the spectrum with the capturing the blade passing frequency at that point to be accurately predicted. And the bottom is internal flow, very common component, which is hydrometer, hydroflow meter, which is used for measuring the acoustic waves, and which has been captured with in this case. Now, what is the advantage of CAE versus the experimental data for underwater is it is very usually the testing in case of the underwater is on the scaled models because you cannot have the complete environment, and also the complex environment variation of the properties is not feasible in testing, and hence CAE becomes a very important part in these type of application also. So I have just touched upon some of the applications, but definitely you can bring up your applications and we can deep dive into them and try to find out the solution. Yeah, thank you. Thank you from my side. Milan, over to you.
Thank you, Banu. So we already ran out of time, but I hope you have a few more minutes for these four next applications that are involving NC sound. So not going into the details of the simulation side, but more in the NC sound post-processing side. With the first example here is the fan noise prediction. So after you do the simulation in Fluent, it's an example for electronic cooling noise. And you first want to, you can create a longer sound from a short duration simulation signal. For instance, Domenico, you can play the sound here on the left, the blue one. Which was the baseline simulation extended, and the green is the modified design. Okay, so longer sound generation. Yeah, okay. Doing a spectrum analysis, of course, comparing also psychoacoustic criteria, and doing some sound troubleshooting, as I showed you in the first video of ANSI Sound, for being able to create some targets using the sound signal modification feature. So as usual, the benefits for this application is to anticipate the noise issues and to save time and money by reducing the physical iterations of the prototypes. Okay, so fine noise prediction is very important topic. The next application is also similar, but it's more related to HVAC noise prediction inside the cabins. So to be able to predict the HVAC noise. Here, this application involves also the sound generation from a short time CFD result at the end of the HVAC here. And also the application of the FRF, so the frequency response function, from the source to the ear of the listener. Yeah. So you apply an FRF, and you can also combine these sounds to create a stereo sound and to predict the sound as if it was listened in the cabin. So the goal here is to avoid doing some heavy simulation of the whole system, which is quite long and complex, but only to apply a frequency response function to a simulation at component level to assess the sound at system level. Right. Here is the third application that we wanted to show with NC Sound is to be able to combine all the sound sources together to assess the noise at system level and to predict the sound of a component at the specific location. Okay, so we take this example of a car where you have sometimes some components, some noise sources that can be more or less easily simulated, and some others that can be better with measurements like rolling noise, for example. Okay, so you combine all those sources into one module called the Sound Composer module, and this is also you have the display of how it looks in NC Sound, but you can also see a video of this module, which is quite important to see actually, because it's been quite appreciated by our users, the Sound Composer module. So here I'm loading a project that I've created, so the video is quite shorter, and you can see, okay, you load all the sound sources that you have simulated or measured. So the first one is the HVAC, electric motor, masking noise, but you can add as many sources as you want. And if you display the final sound, it will combine all those sources and you can assess the sound at system level. Good. So there are different types of sources that you can load. The first one is simply a spectrum. Yes, so we can synthesize a sound from a spectrum using a hybrid method, inverse FFT and peak detection. So you only need to apply a duration to this spectrum and display the resulting sound, which is here quite it's not very loud. But it's a good way to see if the HVAC noise will be heard at the end by the user or not. Electric motor is a different types of source that you input. Here is more harmonic source, which is the order levels versus RPM. So there is no time information, so you need to apply an RPM versus time law to this source, so that it can generate a sound from this. Oh yeah, and apply also a filter, which is the transfer function from the source to the receiver. Okay, so this is the noise of the electric motor, which was simulated with mechanical. And okay, another type of source is the so we can here is the masking noise. It's data set of spectrum. So it's not only one spectrum, but it's several spectrum, and for each of them correspond one control parameter, which is here speed. So there is one spectrum for 20 kph, one spectrum for 30 kph, and by applying etc. and by applying a source control, which is kph versus time, we can interpolate those spectrum and generate a sound from this. So it's quite it's quite a nice feature to have. Masking noise, and finally you can also add one type of noise of source that is directly let's say a time domain signal, so you don't need to do anything with this. So here I've added a kind of turn indicator noise, which can be also heard inside a vehicle. Perfect. So by looking at the final sound and also maybe the time frequency domain, we can see if there is an emergence of one of the source and at which time or which RPM, for instance. As you could see, there is a way to mute some tracks, but also you can call a mix table where you can in real time modify the gain of each track. This is good to know, how much, to what extent you need to decrease one of the track so that the noise can be acceptable. Great. And I have one more application which is quite interesting, which is the drone noise prediction. Also using as input simulation from Fluent. So not with too much details here. Yes, as Domenico is playing, we have the noise at single speed of the propellers, and the goal here will be from these measurements or simulation of the propellers, you can define a trajectory of the drone and an RPM or rotation speed versus time, and to set the type of output where you want to assess the sound. So here it's only a stereo signal. So the goal here is to be able to listen to your simulation in 3D. So it's also one of the features of NC Sound, is to use some headphones or using transaural or VBAP techniques to define all your speakers, location, etc., and use some techniques to predict and to assess the sound in a realistic environment in 3D around the listener.
Thank you, Milan, and I think it was very interesting application. So thank you, Banu. And just to recap, so we've shown some complex acoustic simulation that is possible to do with Fluent, and also we have shown you some of the latest advancement in Fluent, like impedance boundary condition, DAVA workflow. And we have shown this with real case applications. And so we have, of course, worked on much more, many cases because of time and sometimes confidentiality. We are just showing, let's say, a small percentage. And we have also shown, this new ANSI sound capability, which is inside Fluent, but can connect easily with ANSI sound with great, really possibility to do sound analysis. With combining CAE results with operating condition and really ANSYS Sound can add, as you can see, value to your acoustic simulations. So we are happy to to get your comments, or we are happy to get in touch with you for to see if you have any interest in applying this to your use case. Last but not least, also have this new multi-GPU solver for Fluent coming soon. And so with this, I really thank you for your attention, and also thanks to Milan and to Bano for the great presentation. Thank you.